Here's another example that shows the importance of the line width and the beam quality of the laser. In the Nobel Prize-winning work of Ben Feringa and his group at the University of Groningen in the Netherlands on molecular machines, they used Raman spectroscopy to study the rotary behavior and structural changes of the molecular motors in metallic organic frameworks, MOFs. This work was done in collaboration with Wesley Brown, also at the University of Groningen, and was published in Nature Nanotechnology. As they were looking at thermally sensitive and photochemically active compounds, it was found that it was essential to work with a narrow line width laser source with very little stray light and also with very high level of polarization extinction ratio. And finally, we have here an example showing the importance of the reliability and stability of the properties of the laser source in general. This is results from a study made by James Livermore at the Department of Clinical Neuroscience at Oxford University. He was using a Renishaw RA816 Raman system to distinguish normal tissue from cancerous tissue in brain biopsies with very high accuracy by measuring the small spectral variations from these different tissues. And he showed that it's possible to do this in clinical settings in short time, this is less than 15 minutes, and with minimal sample preparation. His study shows that the potential of using Raman spectroscopy to guide surgeons in real time during operations to remove tumors effectively while leaving non-cancerous tissue intact, something that can have a drastic impact on the patient's health. He even managed to classify tumor tissue into specific genetic subtypes. And this is something that can provide very valuable information for surgeons when deciding on tumor resection strategies, as the health benefits of tumor removal are influenced very much by the underlying genetics of the tumor. Another aspect that impacts the requirements on the laser source is what type of Raman instrument it is used in. There is a wide range of different Raman spectroscopy instrumentation technologies and techniques that are addressing different types of applications. We can sort them into three different main groups. There's probe-based Raman instruments that are providing quantitative data used mainly for inline process control and quality control. These systems usually benefit from high laser power, but they usually use multimode fibers and therefore do not require TM00 beams. Then there are very compact handheld instruments used for in-field detection and identification, for instance for homeland security and fraud protection applications. And here the laser should be small, energy efficient to be able to be battery powered. And here eye safety need to be taken into account as well. And finally, there are various types of Raman microscopes that provide high spatial resolution chemical imaging. And here the single transversal mode diffraction limited beam is very important to achieve high spatial resolution in confocal imaging. And it's also usually important here with the capability to eliminate at different wavelengths. So which lasers are suitable for use in spontaneous Raman spectroscopy? There are several types of laser technologies that can provide suitable performance here. One is diode pumped single frequency lasers. These lasers usually provide way less than a megahertz line width emission in perfect Gaussian beams and with a spectral purity well over 60 dB, extremely close to the laser peak. They're available at many wavelengths in the visible, in the UV and in the near infrared, but are less available in the 700 to 900 nanometer region. Most of the lasers in the Cobolt product lines are of this kind, and they're really perfect for low frequency and high resolution Raman spectroscopy. For wavelengths less or not easily accessed by diode pumped lasers, it's common to use various types of wavelength or frequency locked semiconductor lasers. These all have in common that the relatively broad emission from a semiconductor chip is turned into narrow line width or single frequency emission by locking the output to a narrow line width feedback from a grating structure. You get something like this. If the grating structure is integrated on the chip itself, we're talking about DBR or DFB lasers. Alternatively, the feedback is coming from an external grating element. The DBR DFB lasers can be made very compact and cost efficient, but they are a little bit limited in power. The locking with external elements is a little bit more complex, but enables scaling to higher power levels. These lasers can be single or multi-transversal mode beams, depending on the output power. And in order to achieve sufficient spectral purity for Raman spectroscopy, it's typically necessary to use some kind of external cleanup filter so that you get the spectral shape, something like this. So these lasers are suitable for spontaneous Raman spectroscopy with a cleanup filter, but they are a little bit more challenging to be used in low-frequency Raman applications. The semiconductor-based lasers are often more sensitive to optical feedback than the diode pump lasers.